Okay, let's see. We have this equation here. We have w as a function of x, y, z, and t, and then we have this constraint that relates x, z, and t. And they want us to show that the partial derivative of w with respect to x has two possible values depending on what else is independent. So let's just check the partials and see if we can show that this is actually true. So first, let's maybe check dw dx. That would mean x is independent. And this is a relationship between three things. So let's assume also that y and t are independent. Let's see what we get in that case. So let's see. We take the derivative of this with respect to x, we get dw dx. The derivative of x squared with respect to x is 2x. Y we're assuming is independent, so that derivative is 0. And then we get 4 dz dx. And we're assuming that t is independent, so that derivative is 0. All we need to do now is find dz dx. And we can find dz dx from here. So we take the derivative of both sides with respect to x, assuming that y and t are independent. Dx dx is 1. And then the derivative of z would be dz dx, because z is one of the dependent variables, right? T is independent, so that derivative is 0, and the derivative of 25 is 0. So we get that dz dx equals negative 1/2 if we take the 1 over and divide by 2. So plugging that in here, we get 2x plus 4 times negative 1/2, which is 2x minus 2. Oh, so we see that w sub x, the partial with respect to x, is 2x minus 2 in the case where y and t are independent. So this is what they mean when they say wx is 2x minus 2. It must be when you treat y and t as also independent as well as x. So let's try another one, see if we can find out which variables have to be independent if wx turns out to be 2x minus 1. So we'll try dw dx here. Let's try holding y and z independent this time. So we take the derivative with respect to x, and we're going to get 2x, right? And the y is independent, so the derivative of y with respect to x is 0. Y doesn't have to change when x changes. Z is independent, so that derivative is 0. And then we get plus dt dx, right? T, if x, y, and z are independent, then t must be dependent according to this relationship, so we get dt dx. Now we can just use our constraint to find dt dx. We'll just, since we want dt dx, we'll take the derivative of both sides with respect to x and see what happens. So the derivative of x with respect to x is 1. The derivative of 2z, since z is independent of x, the derivative of 2z with respect to x is 0. And then we have the derivative of t with respect to x is equal to 0. So now we find that dt dx is negative 1, and we plug it back in here, and we find that we get 2x minus 1 for the derivative. So when they say w sub x is 2x minus 1, they mean w sub x when y and z are also independent turns out to be 2x minus 1.